this video, I'll talk through the 2024 Advanced Higher Chemistry paper and explain how I would approach each question. Starting off with the multiple choice, we're asked about the outermost occupied orbital in a noble gas. Going to the data booklet will help us with this. Two options for this question. Number one would be to just work out some of the electron arrangements for the different noble gases. First one we've got is helium, would be 1s2. We then have our neon, which is 1s2, 2s2, 2p6. And argon would be 1s2, 2s2, 2p6, 8s2, 8p6. The other option is just to remember the different blocks within the periodic table, where you have group 1 and group 2 as being our S block, the P block being groups 3 along to group 8, transition metals would be D block, and then your lanthanides and actinides down at the bottom would be your F block. Key thing to this question is helium is 1s2, so that's an S block element, even though all the rest of them are P block. It's asking about the whole entire group, so it would be an S or P block element. Next one, we're asked about electronic configurations for the atoms and ions of copper. Data booklet tells us that copper has 29 electrons. First thing I would do is just write out what that arrangement would be for ground state copper. Now, following our trends, this would be what we would expect for copper. However, at this point here, we have a full orbital and then a nothing special orbital here because we get 9 filled out of the 10 potential spaces. In order to become more stable, we would instead have 4s1 and 3d10. We now have a half filled S. We have a 3d subshell that's filled. When it comes to becoming an ion, if we want to have copper 1+, we're going to lose the 4s electron because 4s is filled first and then also lost first. When it comes to copper 2+, we're again going to lose the 4s electron. We would also lose one of the 3d electrons. Walking our way through them, the first one would be copper 2+, the second one would be copper 1+. The third one would have been picked if you hadn't remembered that copper is one of the special arrangements where we're trying to maximize stability. So C is not representative of any of the three choices we've got, whereas the last one is our copper, ground state copper, because we have the filled D subshell and the half filled S subshell, and that gives us C as our answer for this one. In this one here, we're asked about our oxidation states. You need to remember that oxygen will typically be 2 negative. You have 1 oxygen attached, that's going to give a charge of 2 minus. To be 2+ overall, the only way that works is if we have 4+ in our vanadium. It's 4+ and 2 minus gives you 2+ overall. That will narrow us down to B or D. Next, we're asked about an oxidation or reduction. In this one here, we have water as our ligand, which has no charge, so we can kind of ignore all of the waters. The V in this case must be 2+. That's why we have a 2+ on the outside. The charge has gone down. We have been reduced in this case here. So if the charge in a metal goes more positive, it'll be an oxidation as it's losing more electrons. Here, we're gaining electrons and we're dropping the charge from 4+ to 2+, giving us B for number 3. On to number 4. Okay, for this question, we need to remember that the colour we see is the complementary colour to what is absorbed. I'm going to go to the colour wheel to get the colours that would have to be absorbed to see these colours, and also the wavelength that it applies to. Using the information on page 19, we can see to appear purple, it has absorbed green. To be green, it's absorbed purple. To be blue-green, it's absorbed red. And to be red, it's absorbed blue-green. I'm just going to pick the number that's right bang in the middle of each of these sections. So that's around about 530, 390, roughly about 600 odd. Blue-green, we'd got to 5. The largest energy gap requires the smallest wavelength. As the wavelength increases, the energy possessed decreases. Smallest wavelength of the absorbed value would be our purple, which gives us our nickel 2+ as our correct answer. So in this one, a couple of things you need to watch out for. Watch out for the fact that you see the complementary colour. It's the absorbed wavelength that's linked to the energy gap. And then we get our answer from there. Here, we're going to name this particular chemical. We have got 2 chlorines, which would be dichlorido. We have got 4 amines, AMMINE. So that would be tetraamine. When it comes to the order of the naming, we want to have it in alphabetical order by ligand. This means we ignore the tetra and di, and we instead compare amine and chlorido. It would have been tetra, amine, dichlorido. That rules out A and B. Now, the only difference I can see here would be the charge at the end of it. What this is telling us is that overall, we have a 1+ charge. Chlorine is group 7. Chlorine would gain 1 electron to become 1-. We've got 2 of them here. So if you've got 2 times Cl-, we've got a charge of 2. We've got a charge of 2 negative from here. And what this question's asking is, well, what charge on cobalt gives us 1+ overall? Well, it's going to have to be 3+, because then 3+ and 2- overall gives you an extra positive, which makes the overall chemical be positively charged, which makes the overall complex ion positive. And that means D has to be the correct answer. In these kind of questions as well, the fact that it's positive ion overall means we just use the name as normal. So another type of question might have asked you about cobaltate versus cobalt, and there you're looking for a negative charge overall, would have made it cobaltate. But D is the correct answer there. This one, we're going to work out the correct arrangement of xenon difluoride. First thing we need to do is look at the central atom, which would be xenon. Xenon is in group 8, therefore it will have 8 outer electrons. There are 2 things attached to it. Regardless of what they are, we just add on 2. That gives you 10 electrons, and that gives you 5 pairs of electrons. To work out the arrangement around the xenon atom, we don't care about lone pairs or if they're bonding pairs. We just care that we've got 5 pairs of electrons. Now, linear is not what you'd get. Tetrahedral would just need 4 pairs. Got to be trigonal bipyramidal as the electron pair arrangement. The next one, though, is asking us for the actual shape of the molecule. And in this case, we do now care that we have got 2 bonding pairs and 3 lone. And what this will do is this will mean that they will get pushed into a straight line. This will give us a linear shape of the molecule. If visualizing the shapes isn't something that comes naturally to you, PHET, P-H-E-T, have a simulator on their website which allows you to input different numbers of lone pairs and bonding pairs to visualize what effect they would have. We had 2 bonding pairs. Our 3 lone pairs will form a kind of belt around the central atom, and that will keep 2 atoms that have joined in a linear shape. We have trigonal bipyramidal electron geometry versus the overall molecule is a linear molecule. So be very careful about electron pairs versus the shape of the molecule. Number 7, we're asked about propanoic acid. Associates into ions and an equilibrium is established. And page 14 of the data booklet will have that information for us. We're adding potassium propanoate, which means we're adding more onto our right hand side here, which would mean we're going to shift to the left hand side to use those up. Well, in this case here, we had added extra propanoate and we're bringing it back down to the normal value. It's not going to be that one. There would be less hydronium ions because that's now joining up with the extra propanoate to go back to propanoic acid. We are not involving hydroxyl ions, and we'd make more propanoic acid molecules, not less of them. So because we're shifting from right to left, stuff on the right hand side would go down. We added extra propanoate, so that just goes back to normal concentration, whereas we would have less of the H3O positive. Next one. we're asked about the ionic product of water. This is something you can find in the data booklet. On page 20, it gives you the value for it at 25 degrees Celsius. And on page 4, it tells you how you calculate it. Crucially for this question, both the hydronium ion concentration and the hydroxide ion concentration will be equal. That means that our 5.48 times 10 to the minus 14 is going to equal some number squared, because they both have to be the same. So if we want to work out what the concentration of both the H3O plus and the OH minus, we would take the square root of our KW. Give us 2.34 times 10 to the minus 7. Back to the relationship sheet. If you know the concentration of H3O positive, if you do minus log to the base 10 of that, you'll work out the pH. So our pH is going to equal minus log to the base 10 of our 2.34 times 10 to minus 7 is 6.63 as our answer. Water is neutral, so the hydronium ions and hydroxide ions need to be equal, and then that spills out from there. This one, we're repeating an experiment, but we're using a strong acid first, and then we're using a weak acid second of all. Both of the acids, as they have the same concentration, the same volume, and they are both what's called monoprotic, which means they have one proton that they can donate to the base, they will react with the same number of moles of the calcium carbonate. So we will get the same mass unreacted at the end. The time taken for the reaction to be completed will be different because in a strong acid, all of the molecules have dissociated. So all of the H plus H3O positive ions are available to react instantly. So they will react much more quickly. The pH of a strong acid is higher because the H pluses are in solution. And the initial rate, similar to the time, it will go faster because the H pluses are already out. Whereas in a weak acid, as the H pluses get used up, more of them dissociate and it will eventually get to the same endpoint. Just takes a bit longer. This one we're asked about a buffer solution, which we'll find the calculation in the data booklet. We need to have a weak acid and its salt, which we do have here. So we want pH. We'll find pKa in the data booklet. So pKa of ethanoic acid, 4.76. Plug that in, and minus log to the 10. Acid is 0.1. So 0.1 gives an answer of 4.76, which gives us C. I'm making a face because that's the same as the pKa. Yeah, you would just plug the numbers in. Make sure you're putting in concentrations as we're given. They might give you moles and volume and you need to work out concentration first. But here, nice and straightforward, given is D for number 10. Next one, we're asked about what information we can get from here. So a reaction is feasible if delta G is negative. So we have got negative. That'll be that there. There's nothing about delta H being told here, or if it's been favoured by an increase or decrease in temperature. We won't be able to tell that from there. Third order can only be from experiments, which again, we're not told here. And then the low activation energy, we are not told anything about the activation energy, so we can't tell that from there. So these things may well be true, but we can only tell it's feasible as delta G naught is negative. In this one, a change in entropy for the spontaneous formation of the snowflake. Okay, so entropy is disorder. And we're making a snowflake, so a liquid is more disordered, and we're going to become less ordered. So of the snowflake then, it's becoming less disordered, so it'll be a negative entropy change. And if that's becoming less disordered, that must be at the expense of the surroundings becoming more disordered. It's removing energy because it's cooling down, so that energy is being released to the surroundings, so the surroundings would become more disordered. So the total entropy will be the same, it's just going to be going to the surroundings rather than in the snowflake. C should be correct for that one. In this one, we are seeing that the concentration is decreasing over time, and it's just going down naturally over time. This means it will be zero order with respect to A, because it's not having an impact on increasing or decreasing the time taken. It's just progressing nice and smoothly. So with this question, what they are preying off of is if it was rate versus concentration, zero order reaction would show a flat line going across the way, because in this one, the concentration of the chemical has no effect on the rate. In this one though, we're talking about concentration in time. So as a reactant is used up over time, its value would go down. So if it's first order, it'd be going up from the origin up to the right, and then you've got second order where the rate quadruples if you double the concentration. So you've got that curve going steeper than the previous one. So be very careful with which graph you are dealing with. On to number 14. Which of the following can only represent an aldehyde? So if we go to sketch them out, so an aldehyde must have C double bond O and H. There is no other way of representing this. If you tried to put it with a single bond on the oxygen, you would need more hydrogens to put it through. You've got nothing to put the oxygen between to make it into anything else at all. So one, because it's so small, can only be an aldehyde. Let's think of one we can do for number 2. Maybe a double bond between carbons. 1, 2, 3, 4. So carbon makes 1, 2, 3, 4. 1, 2, 3, 4. That would work something like that. If we wanted for C, they just not put a double bond in. That could be an alcohol. There's another option for that one. And then the last one, we could have a ketone with the double bond O in the center with your 6 hydrogens split on the left hand side and right hand side. The first one, that's the only way you can draw that one for there. Propanoic acid, we're trying to look at what kind of chemicals we have. So it would not be produced by the reaction of. Okay. So a bunch of different ones here, right? So we have got an aldehyde and an oxidizing agent. I believe that would work. That's not going to be our answer. Next one here. So failing solution reacts with aldehydes, not ketones. And this is an alcohol. So failings is an oxidizing agent, but not suitable for oxidizing alcohols. That would be acidified potassium dichromate or copper oxide. So I'm going to go for that one there. Here you have an ester, where if we draw this out, you've got to have your C double bond O on the left hand side of it. And then I'll have my 2 carbons coming off here. And on the other side, I've got my O and then 2 carbons. This would be ethiopropanoate. So if you hydrolyze that using water, you would make back the propanoic acid. And then in this one, we've got a nitrile. And we're again carrying out hydrolysis. And hydrolysis from nitriles makes our carboxylic acid. It would be a nitrile with 3 carbons. So it would make propanoic acid for that one. So phthalings, toluenes, and potassium dichromate are ones that are good for oxidizing aldehydes. And here we've got an alcohol. Okay, so our ether would have a carbon on either side of our oxygen. In this case, it would be 2 carbons on one side. So they are both good at dissolving other chemicals. At first glance, I'm thinking it doesn't have hydrogen bonding because it's not got an O to a H. So I would put that one's not right. Substitution using water would work to make an alcohol, and using an alkoxide, which you'd get from reacting an alkali metal with an alcohol. So they are both able to be made from this. Looking at the peaks in infrared, if we go to the data booklet, that peak 3600 to 3200 only happens in alcohols. That is definitely incorrect for our ether for that. Now, they cannot make hydrogen bonds with themselves. There's no oxygen bonded to hydrogen. So having a look back at my notes, what I found is that because they have lone pairs of electrons on the oxygen, ethers can form hydrogen bonds to water, but they can't form it for themselves. So that means the correct answer is D in this question. Answer D is just a straight up read it from the data booklet. So there is no ambiguity there. It does not have absorption in that range because that's just for alcohols and phenols. So when here torn between, as I was, between B and D, D is just written in black and white in the data booklet. So that's the one that I probably would have lent to. I did have to go away and look it up and see exactly why. But that's the lone pairs of electrons on the oxygen allows it to make hydrogen bonds to the water, but it cannot do it to itself. And that would be that. So that's a very tricky one, I would say. On to 17, we're looking for something that reacts with both an acid and a base. This means we're looking for the one that is amphoteric. So we need something that has both an acidic part and a basic part. Let's look for any acidic parts. You have your carboxyl group. Next, we have an aldehyde group. That's not going to be acidic or basic, so that's ruled out for me. On the other side, we're looking for something that's basic. So amine group would be basic in nature. So that one there, and that one there. And then I'm just ignoring your aldehydes, alcohol groups, your carbonyls, and your hydroxyl groups. And that leaves us with C being the correct answer for number 17. On to number 18. We've got two different reactions and we're asked what is the same in both of these. So we would get a cyclic intermediate when alkenes are reacting with halogen. So I would say it would happen in A, but not in, which would happen in reaction 1, but not in reaction 2. A carbocation this time would form in reaction 2, but not in reaction 1. Breaking a pi bond, well, pi bonds are found in carbon-to-carbon double bonds, which only one of them has. So again, it's not that. Heterolytic means that we would be forming positive and negative ions rather than free radicals, which is homolytic fission. So our correct answer would be this one here. Okay, next up, we are given a reaction of alkenes with ozone to form carbonyl compounds, which the following alkenes would produce propanone and ethanol. What I'd probably do here is draw the two things out they're telling us about. I want to make sure I'm keeping the two double bond O's pointing at each other. I'll have my O double bond C, and I'll just make this one prop. So I need to have a CH3 there and CH3 there, and then I want ethanol. Just put H would be there, then we'd have a CH3 there. Going between them, what we're going to do is we're going to get rid of the oxygens and we're going to squish them together by a double bond. So we'd have H going to C, double bond to C, CH3, CH3, and CH3. So looking through what we've got two CH3s. That would work on that side, but the other one has just two H's attached, which doesn't work. Get rid of that. Next one, we have a CH3 and a H, and we've got two CH3s, so that's looking good to me. Problem with the next one, so the issue here in C is we've got a CH on both sides. We only have a CH on one side, so ruled out. And then again, we've got CHs on each side. We're missing an extra methyl group, so B would be the correct answer. So look at the picture, follow the picture, line it up as best you can to what they give you, and it'll make your life a lot easier. Here, we're talking about benzene reacting with chemicals. It's something is reacting with benzene, which has delocalized electrons. That means it will be acting as an electrophile because it likes electrons. So it will go to that ring of delocalized electrons. We're adding in an NO, which means we're going to make our NO2 group. This would be classed as nitration. And we get nitrobenzene would be formed from that one. So our sulfuric acid here is acting as a catalyst. So they'll show us the chemical that's reacting with our benzene. Then the catalyst is shown after the slash for that one. Here we're dealing with cis and trans of a chemical. So we're looking for the 2 carbons that have the bromines on either end of them. In the first one, we've got 1 bromine above and 1 bromine below. Above and below is opposite sides, so that one's going to be trans. And then your second one is going to be cis because they're both on the same side. Looking at the numbers, they are the most important part of this molecule, which means they'll be classed as being number 1 and number 2, which means C would be your correct answer. They have priority over the hydrogens, and that would give you your answers there. So trans, they're on opposite sides, and cis, they're on the same side for that one. Number 22, we're looking for stereoisomers of this compound. So here we've got pent 3 ene 2. Oh, we currently have double bond position 3 because the hydroxyl group takes priority. Now, stereoisomers can be either geometric or optical. It's going to be geometric. We need restriction of rotation, which we have in the double bond between carbons. And to have optical isomerism, you need a chiral center. So that carbon is bonded to 4 different groups: a H, a CH3, an OH, and then the C3H5 on the left-hand side. That would give you your left-handed and right-handed optical isomers. So we're going to have 2 isomers from that. We have the carbon-to-carbon double bond, which means you could have your cis and trans isomers as well. So because it's stereoisomers and it's both of these combined, my answer I'd pick would be 4 for those ones. So we need to be thinking of both types and if they have the necessary parts to have that. So a double bond or a ring like in this one, or we need a carbon attached to 4 different groups. The other one, next one, we're talking about peaks for NMR spectroscopy. Now, H1 is to do with protons, so it's proton NMR, which rules out B and D for me. When we have energy released from these, they show up as a peak. We have flipping of the nuclei. As they then fall back to their ground state, they'll release energy, and that's what's picked up by the NMR machine, and that will pick up as, and that will show up as your spectrum that we have in that one. This one, we have an empirical formula. We're trying to work out what mass of oxygen is going to be present. First thing I would do is turn the mass into a number of moles. 5.128 over 32.1 for sulfur, which we have here. That will give 0.161 moles. Now, our calculation says that it's a 2 to 3 ratio. So if we have 0.161, divide that by 2, times that by 3, gives 0.2415 moles. And then with these ones, we want to times it by the mass of oxygen. This isn't dealing with the O2, this is just the single oxygen. Our mass equals 0.2415 times 16. That will be rounded to 3.8, 3.9. C would be the best answer there. If I hadn't rounded it earlier on or rounded it less earlier on, it would have matched up exactly, but that's the answer that I'd put for 24. Last question of multiple choice. We're asked about the shared fragment for each of these molecules. And what we're trying to do is see if we can overlap them onto each of them. So what we're going to try and do is to highlight the parts that are shown as the options. So let's look at them all together. And we're looking for any parts in any of the fragments that don't appear in all of them. So having a wee scan through for any differences. Okay, so things that I noticed that aren't in all of them. We have NHs here. And you've got your C, your OCH3 on those ones. We don't want anything sticking out of that. That for me rules out B and rules out D. 22. What's the difference between these two? So we're talking about this part here. And I suppose the reason it won't be this one is this is showing that you've got hydrogens around your benzene. So you get your 5 hydrogens because you've used up one of them for that one. Whereas here, you would only have hydrogen on 3 parts, 4 parts for amoxicillin, and then you would have it for 5 for the ampicillin and penicillin G. Because there are groups on here that loses hydrogen, that would rule out that one, which means A is the only one that has them all in it. And that would bring us to the end of the multiple choice. Moving on to section 2. First question is asking about the overall order of the reaction. Both the chemicals involved in the rate determining step have an order of 1. To get the overall, you add them together. So 1 plus 1 gives us second order overall. Next one, we're asked to calculate the rate constant for this reaction. So if we take our equation, that means that K, the rate constant, will equal the rate divided by both the concentrations of the 2 chemicals. Now we're given values, so let's plug them in. Gives us 1.15 rounded to 3 significant figures. When it comes to getting appropriate units, some people just learn what each of them are. I would work it out as I go. We know that we had MOL, L to minus 1, S to minus 1 on top, divided by MOL, L to minus 1 times L to 1. So we have moles per litre on the top, which would cancel out the moles per litre on the bottom. We now want to make everything go to the top line. So we still have S to the minus 1. We've got MOL, which when it raises to the top would become MOL to the minus 1. We have L to the minus 1, which would become L when it comes on top. Rearranging it, I would tend to put it so that the positive one is first. That would be the L. And MOL to minus 1, S to minus 1. You're allowed any order of the units as long as it is the correct unit. So S to minus 1, MOL to minus 1, and L would work as well. That would get us an answer there. Over here, we have to explain which one is the rate determining step. So this will be the one in the rate equation. The 2 chemicals involved are going to be these 2 here. They are reacting together in step 1. Step 1 is rate determining step. Both CH3, CHO, and minus are reacting together. That went on to part B. We're looking for the chiral center. We're looking for a carbon that's got 4 different things attached. It needs to be this one. The first carbon has 3 H's, it's not that. This carbon has 2 H's, not going to be that. And this has a double bond, so it's not going to be that. So our 4 different groups would be the hydroxyl group, got a methyl group, have a hydrogen group, and then we have a C2H3O. That's it. 3 different groups. That is your chiral center. A sample of this is found to be optically inactive. This must mean that you've got both of the isomers of them, but can form optical isomers where one of them rotates light in one direction and the other one would rotate light in the opposite direction. So that's left-handed and right-handed. To be optically inactive, this must mean that it's going to be a racemic mixture. That means it's equal quantities of each enantiomer. Mark there. On to number 2. We're dealing with capsinoids. Chili powder soaked in suitable solvent, filtered, solvent evaporated. Have a property of solvent suitable for this extraction. So if we want something to dissolve in something, they must have similar polarities. So both being non-polar or both being polar. For that one, that's what I'd put for that one. We want fast separation, fast filtration. That would be vacuum filtration. Okay, so this one we're doing a bit of a proportion question here. One thing we need to know that 1 ppm is the same as 1 milligram per kilogram. Or if it was to do solutions, it'd be 1 milligram in a litre. But this is all about masses, so that will work out for this one. We are told that we have 17.4 milligrams in 2 grams. That means that I want to scale this up to 1,000 grams, which is the same as 1 kilogram. So what we can do is if we divided by 2 first of all to get down to 1, and then times it by 1000, that would give us, that gives us 8700 milligrams. And because that's the milligrams per kilogram, that will be 8700 parts per million. And at the top of the question, it says that your Scoville heat value is going to equal that number times 16.1. So in the calculator, it comes out as 140,070. If you were to round them to particular significant numbers, you might go for something like that. Yeah, milligrams per kilogram is important to get this question correct. Next one, we're stimulating a response. That is going to be an agonist. The other type of drug that we deal with are called antagonists. Those are the ones that block the response. So here. Next one, we're told the moles of capsicum in a tube, percentage by mass of the thing in the tube. Okay, so we've got moles of capsicum. Let's make that into a mass. 0.035075 grams. And your percentage by mass is taking that number, divided by the total, times 100. That's going to be our 0.035075 all over 42. 5 times 100. 3 significant figures, 0.825%. There, so a very tiny number of grams in that tube. That would be an answer for that one. Shuffling on, asked about CH3L. Right, sketch this out. Only way this can work is if you have a double bond on the carbon, because carbon needs to make 4 bonds, and without it, that wouldn't work. This is very similar to carboxylic acid, apart from we have an Cl instead of the OH. This is described as being an acid. So the difference in that and a carboxylic acid is it's Cl here instead of OH. Suggests the type of reaction that's happening. Over here, this is an amide or peptide link. We're taking our acid, chloride, and an amine group. This is likely to be condensation. Okay, so this time we are changing what it's reacting with. Okay, to make this easier to visualize, I'm going to point the 2 functional groups that are reacting together at each other. I'm going to have my chlorine pointing towards it. Got my carbon, double bonded to the oxygen, down to the middle carbon, one coming down, up, down. So here we need a small molecule to come off. That's going to be one of the H's from our amine group, and the Cl is going to be lost as well. So when I redo this, have up to our next carbon, double bond O, methyl group, rest of the chain. Work out from that. Next one, to explain how this shows they're arranged in the Pauli exclusion theory. Pauli exclusion theory says that no 2 electrons will have the same 4 quantum numbers. In more simplistic terms, if one's pointing up the way, one points down the way, so all of the electrons in the same box have opposite spins. Because of that, they would have different quantum number. Okay, we're asked for quantum numbers for an electron in the 5s. We have our N, which tells us which shell it's in. So that's going to be N is 5. We then have L, which tells you if it's S, P, D, or F. S has a value of L of 0. If it's P, it would be 1. D, it would be 2. And if it was F, it would be 3. So this value has to go there. Next one is to do with which particular box we are describing. So this is M, L. And if you look at S, there's only one box in each of the S subshells. So we only have the option for 0 for this one. If it was P, you would have -1, 0, or +1. And if it was D, you would have -2, -1, 0, 1, 2, +1. That one. It has to be there. And then your options here for the spin, it doesn't tell you which one we're talking about. It could be first one, could be the second one. You could have either plus or minus a half. So plus 1/2, and then your other option would be with minus a half. That would pick up the mark for that one. Next up, we're talking about emission spectroscopy. How do we get a line? It's about emitting or giving off light. As they fall to lower energy levels, light is given off. This one, we're asked to calculate the wavelength. We're going to go to the data booklet to get the relationship. I'm going to deal with E equals LHC over lambda. The three constants that you need are on page number 20. If E equals LHC over lambda, and lambda equals LHC over E, therefore lambda equal 6.02 times 10 to 23 times 6.63 times 10 to minus 34 times 10 to the power of 8 all over. Because we have joules in Planck's constant, I'm going to make this 251,000. So that's in joules per mole. That would be 4.77 times 10 to the minus 7 meters. Because the question wants us it in nanometers, we need to use times 10 to the power of 9. That will give you 477 nanometers as your answer. Next, we're asked about the coordination number of strontium ions, each one. So you're looking at how many bonds are made to it. Each of them has 2 bonds, has a coordination number of 2. Next, we're dealing with the classes of ligands. This is the dente words, so mono, bi, tri, tetra, penta, hexa, etc., etc. We have got, look at how many bonds each ligand's making. This whole entire thing is our ranolate ligand. It is making 1, 2, 3, 4 bonds in total. Or 4, we would describe that as being tetradente. So the ligand's making 4 bonds. Tetradente. Answer. Next one. We've got a bit of a contradiction, it seems, in terms of accurately, approximately. For that. So we want to measure an accurate mass that is close to 2.5 grams. So if you had something like 2.48, that's close to what we're trying to get, but we have multiple decimal places making it a more accurate result, or you could have 3 decimal places depending on which balance you're using. We want to heat a sample to constant mass. First thing you have to do is heat the sample, typically with a Bunsen burner. You want to cool in a desiccator, which stops the reabsorption of water. So, next one, you want to measure the mass. Heat until the mass stays same or constant. Next one, we have to calculate the mass of N in this compound. That. Okay. 2 things we need to know. So we work out the mass of SrCl2 is going to equal the mass of the crucible with it minus the crucible. That's going to equal 1649, take away 14.7, 1.62 grams. That. And if we work out the mass of SrCl2 with the water, again, that'd be 17.58, take away 14.87. This is 2.71. And that means that the mass of water lost is those 2 new numbers taken away. You want to calculate the moles of each of them. So moles of SrCl2 equal the 1.62 divided by its GFM. So strontium 87.6, chlorine 35.5. 2 of them, so we need to take that into account. That would be 158.6. Our moles of water have been moved. 1.09 Water is just 18, 16 for 16 for oxygen, and 2 for the hydrogens. 0.061 moles. Now we need to try and figure out the ratio between the two numbers and round it, just to make life even more straightforward. Should be able to see if you divide by the smallest number, you would get a 1:6 ratio, meaning that n must equal. So you need to be carefully finding out the two masses, the mass of the chemical without the water and the mass of water that was lost, and that'll give you your answer as you go through it. Next one, we're talking about chromophore. Chromophore is the section that gives a chemical colour. And these ones we're looking for our conjugated system. Here we're wanting alternating carbon to carbon single and double bonds. So we're wanting to grab the part that has the carbon to carbon double bonds one after another. Something like that would pick up the mark. There'll be a bit of flexibility in terms of you grab the options, but it's the double bonds between carbons and the single bonds that we're aiming for here. This one we're looking for an absorption spectrum for a purple substance. If we go back to the colour wheel, then appearing purple means it's absorbing green, which means we want a maximum peak between 560 and 500. What is the graph showing us? 560, 550. 1, 2, 3, 4, 5 boxes, so each one's 20. So 520, 530, round about there would be fine. So we want to make sure we have a maximum absorbance at that point. So coming along, let's spike up here, coming back down, across there. Just double check that too far. Hang on, we're going there. You got a little bit of wiggle room between the 2 points. So as long as your peak is between those 2 values, you'll pick up the mark for this question. Moving on, we're asking about the orbitals for a double bond. A double bond is both pi bond and a sigma bond. So the sigma bond from end-on overlap and the pi bond from the side-on overlap. And these ones we're dealing with the colours of pigments. And these ones with conjugated system, we're talking about HOMO and LUMO. The highest occupied molecular orbital and the lowest unoccupied molecular orbital. And it's to do with the length of the system. So the longer the conjugated system, the smaller the energy gap in the highest occupied molecular orbital and the lowest unoccupied molecular orbital. If it's a smaller gap or longer, I'll just change my wording around there. So we'll go for the larger the conjugated system, the smaller the energy gap, then the longer length absorbed. Number 5 is our first using our knowledge of chemistry question. We're asked about composition and purity of this chemical. But one option would be carry out gravimetric analysis. We could heat it up and it would lose the 3 moles of water, and we could verify that that value matches up to what we'd expect. Precipitation, we turn it into an insoluble product, separate that off, measure the mass of that, and again we can work it back to say, well, we added this much of our chemical, and then that would correspond to a certain number of moles of our original chemical. Another option would be a complexometric titration using EDTA, and that would allow us to determine the iron content of the sample, and again see if it matches up to what it's expected. Another option would be to set it on fire and see what the wavelength of light emitted is. If it's 405 nanometers, then that would show that potassium is present. The intensity of the wavelength as well could give us some indication of the concentration of the potassium within the chemical. We can use melting point apparatus to determine the purity of the sample. If the sample was pure, it would have a narrow melting point range, which would match up to values you could find on the internet or in textbooks. The fact it's green in colour, maybe we could use some UV or visible spectroscopy to determine the absorption peaks to see if they would match the expected results. Perhaps if there's any impurities, the values would be different than expected. Another option would be to use the elemental analysis, where the chemicals combusted and the products made are measured, and then you can work out the empirical formula from those ones for the carbon and hydrogen. For these questions, you get 1 mark for a limited answer, 2 marks for reasonable, and 3 marks for good. Hope this would be in the good category. There's potentially other things we could talk about. Nothing springing to mind for me. So this is what I would end up writing and hopefully pick up all the marks. On to number 6. In nuclear magnetic resonance spectroscopy, it is radio waves that are used to determine the structures of them. The standard reference substance is TMS. Now, luckily for you, it is in the data booklet. At the top of page 17, it describes that they've all been measured relative to the tetramethylsilane, or TMS for short. So if you're ever unsure, go to that page and it will just straight up tell you. Down here, we're talking about a peak at 1.9 ppm. Let's see what that corresponds to. We're going to look at the ones that span past 1.8. This could be an option. That could be an option. That could be an option. Or this. Or this. The bottom two, we do not have nitrogen connected to hydrogen or oxygen to hydrogen, so it's not going to be those ones. We don't have any triple bonds, so it's not that one. Although it could be the CH3 or CH2 next to a carbon involved in the carbon-carbon double bond. We have got a carbon-to-carbon double bond here, which means we are looking for any of the 3 that are in that. The hydrogen that it's referring to is the one that's bolded, so it's sometimes quite difficult to see depending on how old your data booklet is, but we're looking for something next to a carbon-to-carbon double bond. So any of these 3 would be acceptable as an answer. Moving on to part B. Suggest why these are in different environments. When it comes to the environments, it relates to their closeness to other parts of the molecule. If you look at the one at the top, that is in closer proximity to the C double bond O than the one at the bottom. This double bond restricts the rotation around the carbon, and they will then be experiencing different things and end up in different environments. Okay, for part 3, I'm going to strongly suggest you don't do added and just start counting the number of hydrogen environments. Actually, the question, they're talking about carbon. So carbon in different environments will have different peaks. And if we look at this first carbon here, that's a carbon that's attached to 2 hydrogens and then double bonded to a carbon. So that will be its first environment. Now this carbon here has no H's on them, and it's bound to double bonded to a carbon, single bonded to a C double bond O, and then you've got a methyl group coming off it as well. So that, again, is different from the other one. Going down to the bottom, it's carbon joined onto 3 H's. Now, we might think, well, that's the same, apart from the fact this is right beside an oxygen, whereas the one at the bottom is not. So those 2 would be chemically different and show different peaks. And the last one here is the only one attached to an oxygen, and therefore that would be our 5th environment. And if there was another C double bond O, you'd look and see, well, this one here, number 5, is attached to an O CH3, and then a C down at the bottom. And if the other one was different, that would give you a different peak. So there would be 5 peaks in total. And the carbon one, if you did what I did and talked about the hydrogen ones at first, you would probably have said 3. 1 for the CH2, and then this CH3 and this CH3 would be chemically different. But carbon ones would be 5. Next up. Okay, and this next one we're dealing with a different ester, where we've got 4 carbon environments, and we've got 1, 2, 3 hydrogen environments. So the first thing I would do is put in my carbon double bond with my O for my ester link. Okay, if there's 4 carbon environments, it's likely there's going to be 4 carbons. And then that would lead me to think, well, your kind of 2 main options would be something like 2 carbons on either side, or having 3 carbons on one side and then your double bond O with 1 carbon on the other side. Like that. Now, what have they told us here? So there are only 3 different environments. Here you've got a quartet, which means it's going to be next to a CH3. Here you've got 1. That means it's next to no hydrogen. And then here, this will be next to CH. Okay, next we need to look at the relative intensities. Now, in terms of their intensities, if we look up at the pictures up here, they're showing that the 2 on the right have the same number of carbons in them because they're the same height. So I would suggest that those both would be the CH3s, and then this one would be the CH2, because the relative intensities would be lower. If that's correct, then we've got our CH2 next to the CH3. We've got our CH3 next to the CH2. And we have a CH3 not next to any hydrogens. So that looks like that would work out. In terms of each carbon is different. Because yes, you have 2 CH3s, but the one on the left is next to a C double bond O, and the one on the right is next to a CH2. So they are different environments, and then everything else fits in there. So in terms of this one, we have a CH3 next to no H's, satisfies that. We have a CH2 next to a CH3, which satisfies that. And we have a CH3 next to CH2. That actually looks like it would work as well. And the environments are all different because it's a C, H3 next to an O, CH2 next to a C double bond O and a CH3, and then CH3 next to a CH2. So that looks like it could be either of those ones or that. Unless I'm missing something, I would go for either of those 2. Probably the first one more confident in. Here we want the molecular formula. It might be best just to sketch it out very briefly. You'd have your OH group goes to a carbon, double bonded to an oxygen, and another carbon with a CH3 group, another OH on the end. Pop in all the H's that are needed for this. 1, 2, 3, so C3. H, we've got 5, 6. Then O, 3. The answer there. If you've practiced enough, you might be able to do it straight from here and go, well, there's 1, 2, 3, so C3. Then looking at the H's, putting your wee lines on each of the lines to make sure that each carbon makes 4, so you don't need any on that one. And I guess you 1, 2, 3, 4, 5, 6. 4, 5, 6, yep, and then 3 oxygens as well for that. But sometimes it's just easier, just sketch them out. From this one, we are asked to work out pH of a weak acid. I know it's weak acid because it's given a Ka value. Let's go to the data booklet to find out how to do it. So we're going to use pH equals half pKa minus half log of C. We are working out pH, so we'll leave it where it is. It's going to be a half of, we have Ka, so pKa will equal minus log base 10 of 1.38 times 10 minus 4. That again is in the data booklet. Make to be 3.86. So it's going to be a half of 3.86 minus half log to the 10 of 1.12 times 10 to minus 5. So then we pop that into the calculator. And it rounds to 4.41. This one, we're dealing with EDTA. As mentioned in my Using Your Knowledge of Chemistry questions, this is a complexometric titration. Okay, so at the end of this, we want to know the mass of calcium ions. So let's put that over to the right-hand side. And we must be told information about the ethylene diamine tetraacetic acid. We are told the concentration and the average titer value. So we're using N equals C times V. So N equals 0.02 times 14.9 times 10 to minus 3 to turn it into litres. That gives 2.98 times 10 to minus 4 moles. Question says it's a 1-to-1 ratio. Calcium reacts with EDTA. EDTA. Calcium 1. That means our number of moles is 2.98 times 10 minus 4. We're asked about mass. So mass equals N times GFM. Mass equals that number times 40.1. 0.0119 grams. If we want that in milligrams, we're going to times by 1,000 because there's 1,000 milligrams in 1 gram. That'll give you 11.9 grams. Check if there's anything else we've missed. 100 centimeters of milk. That was for 10. Okay, so there'll be that many milligrams in 10 centimeters cubed. So there'll be 10 times as much in the full 100 centimeters cubed. And because we're doing it, scaling it by 10, you could have times the end of the parts by 10. So really, if you wanted to go here, or if it took 14.9 centimeters cubed EDTA for 10 centimeters cubed of milk, then it would take 149 centimeters cubed to get 100. And then you could just run that through without having to do the scaling at the end. Just at some point, you need to scale it up by a factor of 10. On to number 9, we want the equilibrium constant. With these things, it's always the products over the reactants. And we use any leading numbers as our powers. So our capital K, or equilibrium constant, will equal the concentration of SO2 gas squared multiplied by the oxygen gas all over the SO3 gas squared as well. Okay, next up, we're trying to calculate the equilibrium constant. And this is one where we have to see what's happening here. Okay, so we've got our 3 chemicals. We've got 2 chemicals, 1 chemical at the start, and we have 2 chemicals at the end. Now, how I'd lay this out is we've got our start value. We're going to use up some of the reactant. We're going to make some of the products. Then we're going to use our at equilibrium values in our calculation. So what they're saying, we've got 0.7 moles of trioxide in a 1 litre container. So the volume's not changing throughout it. So I'm just going to ignore that for just now. So we're starting off with 0.7 moles of the sulfur trioxide. It says at the end, we've got 0.125 moles of the oxygen. You look up at the top, it's a 1-to-2 ratio. So we must have made 0.125 moles of that, which means we would have made double the number of moles of the SO2, because it's a 2-to-1 ratio. We must have made 0.25 of the sulfur dioxide, which means at equilibrium, we must have the same value. Usually here, we're going to the reactant now. We're going to the reactant now. We must have used 0.25 because it's a 2-to-2-to-1 ratio. At the start, we had no product. We've used no product, and we've not made any reactant. So at equilibrium, we're taking these 2 numbers away, and we're getting that we had 0.45 moles at equilibrium. Then all we'd have to do is to sub these into our calculation. So K equals 0.25 squared times 0.125 all over 0.45 over 0.45 squared. It gets rounded to 0.036. There are no units for the equilibrium constant, so we don't have to put anything there. Here we are starting off with the same number of moles, but we're in a bigger volume. The effect of this having the value of equilibrium constant is a constant. It wouldn't have any effect. So there'd be no effect on the equilibrium constant. Equilibrium constants are at particular temperatures. If you change the temperature, it would have done that. So it's all irrelevant if you don't change the temperature. So just no effect. It would stay the same. Okay, this one, you've got K has a lower value at the second temperature. Okay, so it's always products over that. That must mean then if the value is getting smaller, there's less products. So less product at temperature 2. And it says we have an endothermic reaction forward. That must mean then endothermic cools things down. Endothermic favoured by increase in temperature. If it's not favoured, it has to be a lower temperature. So our endothermic reaction is not favoured for, therefore it's favouring the reverse exothermic reaction, so it must be a cooler, colder temperature for that. So two things, it's important that K is products over reactants, we'll get less product, so the reaction, forward reaction is less favoured, has to be a lower temperature for that one. Next one, we're asked about why there might be a smaller bond angle. When an angle is being squashed, that will be because there will be a lone pair of electrons from the sulfur pushing the oxygens away from each other. So the lone and the bonding pairs, and that results in the smaller angle for the first one. Very slightly smaller, but it is smaller. This, why is zinc not considered a transition metal? Now, zinc and scandium are not considered transition metals because they need to have an incomplete D subshell in at least one of its ions. Zinc has 30 electrons. Going through the usual process about the electrons, we'd get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The Zn 2 plus, they lose the 4s before the 3d. And that's showing that Zn has a full E subshell. It says that's the only ions that they form. So that'll be why it's not considered that. We have a weighed or measured sample of the solid substance. How do we get our stock solution? We're first going to dissolve the solid in a small volume of deionized water. You then want to transfer it with the rinsings to a volumetric flask. You want to make up to the mark with more deionized or distilled water. You want to put a stopper in it and then invert to mix. For the rinsings part, you could talk about putting more water in and then pouring it back in the flask. Just easier to just say transfer with rinsings. Next one, we're trying to get a calibration curve. So we want a range of different concentration stock solutions are prepared. Now, this next part will very much depend on how fancy a colorimeter that you use. Some colorimeters scan through different wavelengths and then display the one that gives the highest absorbance. Otherwise, you need to pick which filter to use. So if it's purple, you want a green filter, or back to front for that one. So suitable filter selected. You would typically run a calibration where you get a value of 0 using your solvent. I think it's more in biology they describe it as being a blank. That one. And then you get the absorbance. Each solution is. Now you plot that on a graph like this, then it lets us do the next calculation, which we'll come to now. Okay, so the question is telling us what value we've got. 0.28 would be one box down. So that would give us 1.4 times 10 to minus 3 as our concentration of permanganate. That's times 0.5. it's 500 centimeters cubed. N will equal 7 times 10 to minus 5. Permanganate is MnO4 minus. There's 1 manganese in permanganate. So when we go over to work out the mass of manganese, we can just use that number of moles as is. So M equals N times GFM. So M equals 7 times 10 minus 5 times 54.9. That gives 3.843 times 10 minus 3. Percentage by mass, we take the mass of the chemical we care about, which is the manganese, divide it by the total mass of the sample, then times that by 100. That rounded to 3 significant figures would give 1.35% as the answer. Next one, we're asked to work out the standard enthalpy change. Enthalpy is delta H. In all these ones, we're doing the sum of the products, take away the sum of the reactants. So delta H naught will equal, well, here is our product. So minus 52.6. Take away, oxygen doesn't have a value here, so we can ignore that. So we're taking away 52.4. That will be minus 105 kilojoules per mole. Now the next one, we're asked about entropy. There's no entropy values here, but there is 2 things. So we can work out to relate delta S to the things that we are told, delta G equals delta H minus T delta S would be helpful. We will have to work out what delta G is. Again, we're doing products, take away the reactants. So let's do that bit first. So the products minus 13. Minus 13.1 minus 60 to 68.2 delta naught goes minus 81.3 joules per Kelvin. That will be kilojoules per mole. As we start to rearrange it, well then delta, then T delta S naught equal delta H naught minus delta G naught, then delta S naught will equal delta H naught minus delta G naught over T. Popping in the numbers, that's minus 105, take away minus 81.3 all over 298, which is the standard condition, and it tells us higher up that it's 298 Kelvin. Pop that in, that will give minus 0.795 kilojoules per Kelvin per mole, or times that by 1000 to get minus 79.5 joules per Kelvin. Now, reaction becomes feasible when delta G naught equals 0. So we're going to base it off of this equation again. So we've got set, so we're going to set delta G naught to 0. So take across, you've now got T delta S equals delta H. So then T equals delta H naught over delta S naught. Watching out for the fact that we've got joules for delta S naught and kilojoules for the other one. I prefer to turn my enthalpy into joules, so times that by 1000. So it would be minus 105,000 over our minus 79.5, and then popping them in into 3 significant figures, 1320 Kelvin as the temperature for that one. Next up, we're looking at the state that these things are in. We have a solid with the gases. They are in different states. That's heterogeneous catalysts. In a question that I suggest, it's not one of our typical type of reactions that we've looked at. It'll be a slightly tweaked version of the chemicals that we've talked about before. In this one, we're adding water. which perhaps could be something like a hydration reaction, depending on the makeup of the original chemical. Another option perhaps would be something like a hydrolysis. Now, in terms of this chemical, epoxy, if I remember correctly, the one where you'd have your 2 carbons joined up to an oxygen, something like that, and then over here we've now got 2 hydroxyl groups on here. So if we're splitting apart a substance to make a new substance, hydrolysis to me maybe feels a bit better for that one. But yeah, probably what I would go for there. We need to draw what we are making here. We have to draw the skeletal structure, so let's just draw it out normally. So we've got our OH going to, and you get 2 sets. This and H3 on the end. How on earth is that going to go? Right, so the OH attached to H to H to O. And just go again, maybe? So CCO. The CH3 has to be on the end because that's the only way you can get 3 hydrogens on it. Dealing with our repeating unit there. Not too convinced about this, but let's try it anyway. So we've got our carbon next to the OH. Then got our second carbon, which is this one here, up to an O, down to another carbon, back up to another carbon, down to an O, and out to a carbon from there. Only way I can see it working, because you need that. The oxygen's got an extra bond to make. That'll be the part that joins onto the next one. So in my head, I'm thinking that would be CH2, CH2O number 1. And then this would be CH2, CH2 number 2. Then you get your CH3 as well. We get the rest of them in there. Something like that, perhaps. Next one, a little calculation to work out the formula if n equals 3. Wow, right, okay, so we've got 3 in there. So let's just make a wee list of left-hand side. So we've now got, we had 2 carbons, we've now got 3 equal to 6. We had 4 H's there, so that's 12 H's plus the 3 there, makes it 15. And then we'll get 3 oxygens, and we've got n equal to 1. Then n is 3. Well, then 3 minus 3 is 0. Now, I'm a little bit lost here because if I look at this thing here, if n was 3, then 3 minus 3 would be 0, which would knock away any of that. That's not going to work because we need 1 nitrogen and the other one for that. So the 3 over here works because you have got 2 carbons and then you have 6, which is what we want. Inside that, you'd have 5 H's, which times by 3 gives you 15, so that works. And then you'd have 3 oxygens, which works. It's the nitrogens that I'm a bit lost with. Going off of like the basic chemistry thing of left-hand side has to equal right-hand side. And the only way this could work is if you had on the other side, on the right-hand side, C6H15, whatever way around you want to do it, but NO3 for that. Trying to fit it into what they've got, what would you end up with? Like N in front of it, and then have your CH2, CH2, OH, the 3 there. Like I say, the nitrogen bit's bothering me. Just last time I checked, 3 minus 3 is 0. That would knock away any nitrogens at all. So I'm potentially missing something there, but that seems a wee bit confuddled by that. Okay, moving on to number 11. calculating mass of this, need to get this titer value, right? So for the NaOH, we have concentration and volume. So let's deal with that. First of all, 3v.1 times 15 times 10 to minus 3 to turn it into litres, which would be 15 times 10 to the minus 4. Now the ratio is 1 to 1 for our QHP. And if n equals that, then m equals n times GFM. M equals number of moles. So we first need to count the number of carbons. We've got the 6 carbons in the ring plus these two here. That would be C8. There would be a hydrogen on the points that are not connected to something else. So that's 4 plus that one would be 5. So H5. Oh, there's 4 and there's 1K. So we've got 12 for carbon. So 8 times 12 plus 1 times 5 plus 4 16s plus 39.1. There. 204.1. Multiply that by our number of moles. 0.36 grams is our answer for that one. On to part A, part 2 here. I would use this to select a suitable indicator. So the indicator should have a range within the vertical part of the graph. Now, if I line this up, so we want something that would change colour within that sort of range. Now, they're accurately measured out the masses of the two different samples. So the likelihood is they would have different masses of the samples. That would give you different required titration values. And that's why they wouldn't match up for that. So each sample may have a different mass. So that goes back to the whole accurately, approximately. So they'll be around about the same number, but we'll know exactly what they were. Next one, why does the mass of KHP increase as purity decreases? For that, so sum of the mass would be due to purities. So when you measure out, so if we go to the one that's here, when you measure out that much, it wouldn't be that much of the pure KHP. It would be mostly that, 99% of that, but also the 1% of the other stuff. Concentration carbon, 150 centimeters cubed, 0.67 grams, purity of 99.5. Lovely. So we're dealing with the 99.5%. So that would require KHP go to 2.137 grams. Now we have only got 0.67 grams. So that is for 1 litre of 1000 ppm. So if we wanted 0.25 of 1000 ppm, is 250, we would need a quarter of that over 4. That would be 0.534 to 5 grams. Right. So 0.534 grams. Get about that for a second. Would have a value of 100,000 ppm. And we've got 0.670 grams. Go through 1, because you can just divide by the first number to get down to 1. And then times by the second number, give 0.670. and do the same to the ppm on the other side. It should be a bigger number. So what did I do? I scaled it down to see what I would need if I was keeping 1,000, the same concentration, but for a quarter of the volume. And then I've scaled it up because we have got more than what was needed to make 250 of 1,000. So if we use more of the KHP, that would represent a higher concentration of carbon. There's probably a more elegant way of doing it, but I think that's what I'd end up doing there. Molecule X, well, we have carbons. We have 3 carbons in a row. We have a methyl group. OH on the first one, and the methyl group on the second. So 2 methyl propan 1-ol. Next one, we're trying to make an alcohol from an alkene. Well, water. So to carry out a hydration reaction, we would want an acidic solution to be able to react them together. Okay, so I'm going to just draw it out fully to help us visualize what's going on. Yeah, see there. Our 2 H's on there. There. When this breaks, we're going to end up with 2 new bonds coming off the carbon where the double bond was. And we are using water to carry this out, which is going to be our OH and our H. Markovnikov's rule is the one that states when you are breaking carbon to carbon double bond, the hydrogen goes to the carbon that already has the most hydrogens. And that means that we would want to draw the OH in the middle of the chain and our H on the end carbon, which has already got 2 carbons on them. And we would have that. Go back to skeletal. So we get a carbon coming down to the center. We're coming off. We'd want 3 carbons in a row. Carbon off of this one. OH off of this one. 1, 2, 3, 4, and that works out quite nicely for that. Why would it be minor product? The intermediate, it's always about the intermediate. Intermediate is less stable. So we form, so a less stable carbocation intermediate is made. And this one we're going to be making a free radical and homolytic. So each atom takes 1 electron from the bond. So that can be shown with the single-headed arrow showing that each atom takes 1 electron from that. And this one we have a bunch of different products that could be made. You'll end up with a mixture of different products would be formed. Because when you get to the middle thing, that could go further and make your alkene for that. So some of it will do that, which lowers the yield that we can produce. Final question, second, using your knowledge of chemistry question. A lead on from the one before. So the fact that it says discuss some of the reactions means that there must be different ways we can get to that. Esters from higher, we talked about alcohols and carboxylic acids. Here we have a haloalkane. Okay, so one option would be to do a nucleophilic substitution reaction using aqueous sodium hydroxide, forming your secondary alcohol. You could talk about SN1 versus SN2. Tertiary can do either. The primary one is more likely SN2, and tertiary SN1 is more likely for that. Once you get your alcohol, you could react with carboxylic acid in a condensation reaction. This requires a catalyst using concentrated sulfuric acid. Another way of making the esters would be using the acid chlorides to react with the alcohols to form the ester, and that's faster and does not require a catalyst. It makes it different. Yeah, I've been kind of racking my brain to see what I could do for this. You could turn it into a nitrile, and then hydrolysis of the nitrile would make the carboxylic acid, and the carboxylic acid could react with an alcohol to form the ester. That would be another option. There's very much might be more things you can talk about. Going off of the limited, reasonable, or good, I'd still be quite confident I'd get into the good category, not quite as strongly as in some of the other questions, but I can't at this moment think of anything else. So I'd end that question there. That brings us to the end of the paper. Thanks for watching. Goodbye.